Now we will see here isolated square footing, manual design and Excel sheet, and also we will compare with the safe results. Okay. So isolated square footing. Here given values are dead load 700 kilonewton, live load 300 kilonewton, width of column 230 mm, depth of column 230 mm, and FE 500, M20 grade of concrete, SBC is 250 kilonewton per meter square, allowable settlement is equals to 25 mm. These are the given datas. Now we will start manual calculations. Before that I will draw this is column and this is footing. Okay, this is ground level, and here dead load plus live load, it means 700 plus 300, total 1000 kilonewton load is coming from the building. Okay, right. Now our first step is load calculations. Means dead load is 700 kilonewton, live load is 300 kilonewton, our total load is 1000 kilonewton. We will assume self weight of footing. How much? 10% of dead load and live load. Okay, so 10% of 1000 kilonewton, it means how much it is? 10 by 100 into 1000. 100 kilonewton is self weight of the footing assumed self weight of footing. Okay, now our grand total load, how much it is? Grand total load is dead load plus live load plus self weight of footing. How much it is? Dead load is 700, live load is 300, and self weight of the footing is 100. Total 1100 kilonewton. This is total load transferred to the soil. Here you can see this 700 plus 300 kilonewton load is transferring till this. It means till up to the footing level, and then this extra self weight of this footing and this dead load plus live load of the building, these both we have to add, and the total load will be transferred to this soil. Okay, so how much it is? 1100 kilonewton. Okay, now second step is footing area calculation. Now we know the how much load is transferring to the soil. On that basis we will calculate the footing area. So area required here, dead load plus live load plus self weight of footing divided by SBC. Dead load how much? 700. Live load 300. Self weight of footing 100. SBC how much it is? It is given in this area. SBC is our 250 kilonewton per meter square. So what I will do? 250. These all loads are in kilonewton, and this SBC is kilonewton per meter square. So what happens? This kilonewton into meter square divided by kilonewton. Kilonewton get cancels, and area will be in terms of meter square. So how much it is? 1100 divided by 250 is 1100 divided by 250, 4.4 meter square. So area required is 4.4 meter square. Okay, now how to distribute this area? If we have square column, then footing also we will provide in the square shape. Okay, so what we will do? Square footing, for the square footing we will do under root of area required. It means under root of 4.4. How much it is? 2.097. Okay, so this is square footing area calculation. Okay, 2.097. So what I will do? I will give this one as little more, 2.3 meter. So length of the footing and width of the footing is 2.3 meter. Okay, so provided size of the footing is, therefore provided size of the footing is 2.3 into 2.3 meter, and area provided will be how much it is? 5.29 meter square. Okay, so now our diagram will be like this. This is 2.3 meter, this also 2.3 meter. Here load 1000 kilonewton, and this is transferring like this. When we are applying this load on the soil, then we get reaction from soil also. Okay, so how it is? The reaction is like this. So this reaction is our soil, upward soil pressure, upward, what we call it as upward soil pressure. It should be less than SBC of the soil. Okay, so now how to calculate the upward soil pressure? This is our step 3, upward soil pressure calculation. So what is the formula? Dead load plus live load plus self weight of footing divided by provided area of footing. How much it is? Dead load is 700, live load is 300, self weight of footing is 100 kilonewton. Provided area of footing is how much it is? 5.29. So how much our upward soil pressure now? 1100 divided by 5.29, 207.93, 207.93. This one is kilonewton and this is area, right? So meter square. So upward soil pressure in terms of kilonewton per meter square. So I will write it as round of 208 kilonewton per meter square. So this one is less than our SBC. How much is our SBC? SBC is 250. This is less than SBC. SBC is 250 and our upward soil pressure is 208. Hence it is safe. Okay. Now next step. Step 4. Now what we did? First we calculated how much total load is transferring to the soil, and then on that basis we have calculated the how much area required, and then on that area we used the square root of that area to calculate the length and width of the footing. And then what we did, area provided, how much we provided the footing area, length into width, we calculated as area provided. On that basis, area provided, we calculated the upward soil pressure, which should be less than SBC. Hence if it is less than SBC, then it will become safe. Okay, now we will calculate the depth of the footing. This is our footing. This one is length of footing, how much it is? 2.3 meter. And this is width of footing, how much it is? 2.3 meter. Now what we have to find out? This depth of footing, how much? To find out how much depth is safe, it depends on the two criteria. First one is flexure and second one is shear. These two criteria are very important to find out the depth of the footing. First we will see flexure. First one is flexure. This is our footing, and due to this load and this self weight of the footing, the loads are transferring to the soil here on this soil. What? Due to this load we get reaction from the soil. Due to this reaction, footing slab will get deformed. How? You can see here. Like this. Okay. So this is stiff area. Okay, come back to this point. Due to this reaction of from the soil, the footing slab will get deformed. Here you can see deformed. This deformed response is called as flexural behavior. Flexural behavior. Okay. Due to flexural behavior, maximum moment will be developed at the face of the column. Where? Here. At the face of the column, the maximum moment will be developed. This is maximum moment. This is face of the column. So I will write here maximum moment will be developed at base of the column. Okay. To resist this maximum moment, how much depth is required, that we have to calculate. Okay. To calculate depth, we need first maximum moment. So we have to calculate maximum moment developed in x direction and y direction. Now let's understand the x direction and y direction also. Okay. So this is our thing. Here x direction and this is y direction. Now moment we will see. This is our x direction and moment will be developed at the face of the column. So here is maximum moment at the this face of the column. This is along x direction, we can say. Okay. And this is face of the column and this one is y direction and moment is like this. Here is maximum moment developed at this face of the column and I will call this as along y direction. Okay. But ours now in this situation, ours is square footing and square column. So both x and y are same. So our projected span is same for x and y direction. Let's calculate the projected span. If this is 2.3 meter. Okay. This also 2.3 meter. Right. Our column dimension is how much it is? 0.23 meter, 230 mm, and this also 0.23 meter. Now how to calculate? Projected span is equals to 2.3 minus 0.23 divided by 2. How much it is? 1.035 meter. So this is 1.035 meter and this is 1.035 meter. Similarly, I will extend this one. 1.035 meter, 1.035 meter. Okay. Here this is stiff area. This portion, this stiff area portion won't influence because this area has infinite stiff, so it won't get influenced by the action of the column load. This column load, it won't get influenced by this column load 1000 kilonewton. Okay, so our this portion, only this portion is flexure by the load, so we can say this as cantilever portion. Okay, but it is upward direction, in upward direction, opposite direction. Okay, so our dimensions are, this is projected dimension, how much it is, 1.035, 1.035, and this one is 0.23. Total how much it is, you can check this 1.035 and sorry 1.035 plus 0.23 plus 1.035, 2.3. How much we have provided the length and width of the footing, 2.3, so it is correct, 2.3, right? And the this upward, oh, here I will do draw upward soil pressure, how much it is, 208 kilonewton per meter square. In plan you can see like this, how much, you can see in plan this portion, this cantilever portion is here. Okay, how much it is, 1.035 meter. Now we will calculate the moment. How to calculate, we have square footing, so moment in x direction and moment in y direction both are same. For that purpose I will calculate only one time moment. So cantilever formula is W L square by 2. Okay, so W is net upward pressure. Here I will take the width of the footing, total width of the footing, this one, total width of the footing. So our W will be net upward soil pressure into total width of footing. So how much it is, 208 into 2.3. This one is kilonewton per meter square and this one is in terms of meter. 1 meter get cancels, the answer will be kilonewton per meter. The answer will be in terms of kilonewton per meter. So how much it is, 478.4 kilonewton per meter. So approximately I can say this W as 479 kilonewton per meter. Okay, so here W will be 479 and L square means this one is L square. How much it is, 1.035 square divided by 2. The answer will be 256.55 kilonewton meter. How, this one is in terms of meter square and this one is in terms of kilonewton per meter. 1 meter get cancels, so kilonewton meter will be left. So our final mx and my approximately 257 kilonewton meter. Okay, now I will factor this moment, then mux and muy. How much it is? 257 into 1.5. The answer will be 385.5 kilonewton meter. Mu, x and y. Okay, now we calculated the moment. How much moment, maximum moment will coming at the face of the column. Now the formula for depth calculation, D, what is the formula? T is equals to, no, I will try to explain like this. If our grade of steel is Fe415, here we have considered Fe500. So I will say this one also. If our grade of steel is Fe415, then the formula will be Mu is equals to 0.138 FCK BD square. If our grade of steel is Fe500, then the formula will become 0.133 FCK BD square. Okay, so in our case we have Fe500 grade, so I will use the 0.133 FCK BD square formula. So for this, how to find out the D? D will be under root of Mu by 0.133 FCK B. Okay, now Mu will be, how much it is Mu? 385.5 under root of 385.5 into 10 to the power 6 divided by 0.133 FCK. How much it is? M20 grade, so I will use 20. And B is, how much we have considered the B value? Full width we are considering here, so 2300 is our B value. Okay, so this 10 to the power 6 is how kilonewton meter is our 385. Mu will be 385 kilonewton meter. So for kilonewton we will do convert it as Newton by using 10 to the power 3, and for meter 10 to the power 3 mm. So what happens? 385.5 into 10 to the power 6 Newton mm. Okay, and these are also in this 20 is Newton per mm square, and this 2300 is in mm. So what happens? This 1 mm square, 1 mm will get cancels, and left is Newton per mm is left, and here Newton mm is left. So what happens? Newton mm multiplied by mm by Newton. This get cancels. Something I did wrong, I think so. So no, it's mm square only. Right. Okay. This mm into this Newton get cancels mm square. So it's under root there. So what I will do? I will the square root and this mm square will get cancels, and rest will be the mm. So what happens here? How much it is? The answer will be 251.01 mm. D, this one is D required. Okay, so I will round off this one as 252 mm D required. Okay, this is the depth. This is depth required for flexural. Okay, now for shear depth required is more. So what I do, I will assume almost the depth required for flexurals double, more than double require to pass the shear value. So what I do, I will take depth required as capital D is 600 and clear cover I will assume this as 50 mm for footing, and dia of bar I will use dia of bar 12 mm I will use. If required later we will change it. Okay, so what happens now, effective depth will be how much it is, 600 minus 50 minus 12 by 2. How much it is effective depth, 544 mm. D effective, this is our D effective. Now what we will do, we will calculate the AST, area of steel we will calculate. Here the formula for this AST is 0.5 FCK divided by Fy 1 minus under root of 1 minus 4.6 mu divided by FCK B D square multiplied by B into D. This is effective depth and this B is considered width. If you considered 1 meter, then you have to take 1000. If you considered full width, so we considered full width of footing, so I will take this as how much it is, 2300 only. Okay, so I will solve this one. FCK is our 20 and Fy is 500 and 1 minus under root of 1 minus 4.6 mu means how much it is, mu we already calculated here, where it is 385.5 into 10 to the power 6. Okay, so divided by how much it is, FCK means, sorry, not for this, divided by, we need only for this. Okay, FCK means 20 and B means 2300 and D effective depth means 544 square. Okay, and multiplied by how much it is, 2300 into depth is 544. The answer will be, you can calculate this one. I will write here the answer. How much got the answer? 1701.63 mm square, approximately 1702 mm square. Okay, this is AST required. Okay, now we got the AST required. We have to find out the AST minimum. How much the AST minimum for the footing? 0.12%, 0.12% of B into total D. How much it is? 0.12 divided by 100 into B means 2300, D means 600. So AST minimum required is 1656 mm square. AST minimum. Okay, so we have to compare these both, AST required and AST minimum. Whichever is maximum, we have to take that AST. Okay, if AST minimum is maximum, then we have to take the AST minimum value only. So our AST considered is how much now? Now which one is maximum here? 1702. This is max AST. So now we got the AST. Now we will calculate the spacing required over the width and length. How? Spacing required is pi by 4d square divided by max AST, which we have already compared that one. So I will take it as considered max AST. Okay, into total width of footing. Okay, so how much? V pi by 4 d square, how much we have assumed here? 12 mm we have assumed. Okay, so 12 square, and maximum AST is how much? This is maximum AST 1702. So 1702. Total width of the footing we have considered 2300. The answer will be spacing required is 152.83 mm. This is S required. Okay. Now we will round down the spacing and we will use as S provided. How much I will provide? 100 mm I will provide. Okay, you can check it at the 125 mm also. 25 mm round down you can do. Okay, so if 100 mm we are providing means how much AST provided? Here this is AST required. Area of steel required 1702, but we are providing at the 100 mm center to center spacing. So how much will be the AST provided? We have to calculate. The formula is pi by 4 d square divided by spacing into considered total width of footing. Okay, so pi by 4 d square means 12 square we have considered, and spacing is 100 and 2300 is width of the footing. The provided AST provided is how much? 2601 mm square. Required is 1702, but provided is 2601 mm square. So here AST required should be less than AST provided, then it will become safe. How much AST required is 1702 and one provided is 2601. So it is satisfying the rule. So hence safe in flexure we can say. Okay, so we will find out the percentage of steel provided also. It will helpful to us in future steps. So I will calculate this PT required is AST considered maximum AST considered divided by B into D. How much it is? 1702 2300 into 600 into, it is in terms of percentage, so 100, so 0.123%. Okay, so similarly this one PT provided, how much it is? PT provided is 2601. B means 2300 into 600, all same, nothing is changed, only AST considered is changes here. So how much it is? 0.188%. Okay, so we have calculated PT also. Now we did flexural, this step, flexure step, we have calculated moment and D required and AST provided, required, all we have done. Now we will do shear check. In shear, first we will calculate the one way. You can check two-way shear also first. After two-way shear check, one-way shear will be almost all time it will pass. Okay, so but still I will calculate one-way shear first only. So this is one-way shear will be at D distance from face of the column. Okay, this is critical section present from the face of the column to distance D, effective depth. Okay, so this critical section, this is our critical section. In one-way shear we find out nominal shear developed at the critical section. First we will find out nominal shear, it means tau v, and then we will find out the same, for the same place we will find out the capacity of that section, that is tau c, and then we will compare. If tau v is less than tau c, then it will be pass. If it not matches the this tau v, it means, I mean to say, if tau v will be greater than tau c, then what we have to do in this case? We have to revise depth and reinforcement. Okay, so first we will find out shear force at critical section. This is 208 kilonewton per meter square, and this is d distance. This d is effective depth. How much it is? 544. Now this is A and this is B. Both are 230, 230. Okay, so our diagram will become like this. This is 230 and this is 1035. This one is 1035 mm, mm, mm. Okay. Now we will find out the shear force on this critical section. Okay, so shear force at critical section, formula will become net upward soil pressure into total width of footing into length of footing minus size of column divided by 2 in minus b. This is our formula. Okay, so net upward soil pressure is 208, total width of footing is 2.3 and length of the footing is 2.3 minus size of the column is 0.23 divided by 2 minus d means 544, 0.544. How much will be the answer? V is equals to 234.89 or approximately 235 kilonewton shear force. Now multiply by 1.5. 235 into 1.5, how much it is? Vu will become 352.5 kilonewton. Okay, so now we will find out the tau v value, nominal shear value. How? Tau v will be Vu by Bd formula. Okay, Vu is how much it is? 352.5 multiplied by 10 to the power 3. B means 2300 and D means 544. How much it is? 0.281 Newton per mm square or MPa. Now we will find out the tau c value. How to find out this tau c value? For that we need PT provided. So PT provided, how much it is? How much? Here it is. Here PT provided is 0.188%. So I will do here PT provided is 0.188 percentage. Now what we have to do? Let's go to the IS 456. Here this is table 19. In table 19 our percentage is 0.188. It falls under how much it is? 0.15 and 0.25. In between this it falls. So what we have to do? Let's say this is PT and this is M20 grade. Okay, So how much it is? 0.15. Ours is 0.188 and other value is 0.25. So we have to interpolate the values. How much it is for M20? 0.15, 0.28, and 0.25, how much it is? 0.36. So I will write down here 0.28. This one is don't know, and this one is 0.36. So this is the tau c value, ours. Okay. So how to calculate this? I will say here. Click on the mode, and then here what it is? 3. So I will click on 3, and this one, second option, a plus bx, second option. Here in x value, how much we have? 0.15. 0.15, enter, and 0.25, enter, and let's go here. In front of the 0.15, how much it is? 0.28, and in front of the 0.25, how much it is? 0.36. 0.36, enter. Okay. Now click on AC and enter how much, for how much value we need the tau c value? 0.188. So click on 0.188 and click on equal to, and then shift, enter, 1, enter. Sorry, something missed, we have missed, so I will do another time. I think it's too late for that. Change the, so click on mode, 3, 2, 0.15, enter, 0.25, enter, and this is 0.28. This one is tough, so I am showing for you, and 0.36, enter. Now AC, enter, 0.188, enter, shift 1, okay, shift 1, and here this one option, fifth one, and this one also fifth one. So what I have to do? Enter 5 also and enter. Here is the answer. How much it is? 0.3104. It should be in between 0.28 and 0.36. How much it is? 0.3104. So our tau c value will be, how much this value? 0.3104. So our tau v is less than tau c or not? How much tau v value is? 0.281. Tau v is 0.281. This is less than 0.3104. So hence provided depth is safe for one-way shear. Hence safe for one-way shear T provided. Okay. So let's calculate two-way shear check. Just wait a minute. Okay. Now we will calculate the two-way shear check. We call it as also as a punching shear. In this two-way shear, we will consider critical section at a distance of d by 2 from face of the column. Okay. So this is our diagram. From face of column d by 2 distance, two-way shear will become critical section. Okay. So here this also d by 2, and this one is a column direction, okay, dimension. So what happens? This is d by 2, this is column dimension, and this is d by 2. Similarly in this side also, this is d by 2 distance, and this one is column dimension, and this one is d by 2 distance, okay. Now this d by 2 will become d, so the formula will become a plus d. Here b plus d, d by 2 will be d, and b is column dimension. So how much it is? This is our column dimensions is 230. So this a dimension is 0.23, and depth is ours 544 mm, 0.544. So the answer for this is 0.774. This one also same, 0.23 plus 0.544. How much it is? 0.774 in both direction. If our column dimension is changed, then this dimension will become change. If our footing dimension is change in length and width, then also this dimension will become change. Calculation will be we have to do for both direction, okay. So now how to calculate this perimeter area? How to calculate this perimeter area? Till here the dimension is 0.774, we already calculated, and this also 0.774, and this total we have 2.3 meter, and this also total we have 2.3 meter. The perimeter area will be how much? Perimeter area is equals to total area of footing minus internal area of footing. It means total area is 2.3 into 2.3, 2.3 into 2.3, and internal area is how much it is? 0.774 multiplied by 0.774, okay. So the answer will become 4.691 meter square. Please calculate you also. This is perimeter area 4.691. Now we will calculate the shear force. Shear force, net upward soil pressure multiplied by perimeter area. How much it is? 208 multiplied by perimeter area is 4.691 meter square. 4.691 meter square. So this is in terms of kilonewton per meter square, and this one is in terms of meter square. This meter square get cancels. Shear force will comes under in terms of kilonewton. How much it is? Multiply 208 into 4.691, 975.72 kilonewton V, approximately 976 kilonewton. This is our shear force, and VU will become 976 multiplied by 1.5. How much it is? 1464 kilonewton VU, okay. Now let's find out the tau V value. Tau V is equals to VU by B dash of T. Here B dash means perimeter length of shear area. It means this area. This is 0.774, 0.774 this area, and this one 0.774, and this one 0.774. How much it is? This one is P. I will call it as P, Q, R, and S. P plus Q plus R plus S is our perimeter length of shear area. How much it is? 0.774. 3.096 meter. Okay, so our B dash will become 3096 mm. Okay, so the value will be, VU is, how much it is VU? We already calculated it here, 1464. 1464 in terms of kilonewton. B dash is 3.09. So I will do this one in terms of Newton into 10 to the power 3, and I will do this one 3096 into D is 544. How much? The answer will become 0.869 Newton per mm square. This one is mm, this one is mm square. So tau V will be Newton per mm square. Now for tau C, before tau C we have to check one clause where it is present. The clause will be 31.6.3. Here, permissible shear stress. When shear reinforcement is not provided, the calculated shear stress at the critical section shall not exceed Ks into tau C. Now Ks formula is, where it is here, Ks formula is 0.5 plus BC. BC means short side of the column dimension divided by long side of the column dimensions. So what happens in our case? And tau C will be 0.25 under root of FCK. So in our case, let's calculate. Here we have to check the IS 456, page number 58, clause 31.6.3. okay, Ks into tau C. Ks is equals to 0.5 plus of beta C, where beta C is short side of column dimension divided by long side of column dimension. In our case 230 by 230, so it is 1 beta C. Okay, so now our Ks will become 0.5 plus 1. 1.5 will be the Ks value. But one criteria is present in the code book. Ks should not be more than 1. I think it's here only. Here Ks 0.5 plus beta C, but not greater than 1. Code book says it should not be greater than 1. In our case, what happening here? 1.5. So for this reason, for this code book reason, we will take Ks value as 1 only. Ks is 1 because of code book. Okay, Ks is equal to 0.5 plus 1, but it should not be greater than 1. Okay, so now tau C formula is how much? What is the formula for the tau C? Tau C is equals to 0.25 FCK. 0.25 under root of 20, 1.118. This is our tau C. But we have calculated the Ks value also. Tau C is equals to this Ks into tau C. Ks means 1. Tau C means 1.18. So the value will be 1.18 tau C. Okay. Now how much it is? Tau V value, how much we got? 0.869. Tau V is 0.869 and tau C is 1.118. So tau V is less than tau C, hence safe in two-way shear also. So our final detailing is like this. This is upward soil pressure. How much it is? 208 kilonewton per meter square. The depth provided is 600 mm, capital D. This one is okay. And similarly, reinforcements. I will denote like this. In this case, in our case, both are same. So how much we have provided already? You know, T12 at 100 mm. Where it is? Here it is. 100 mm. AST provided is provided is 100 mm, and 12 we have taken the dia of the bar. So our detailings is like this in both direction. T2 square, T12 at 100 mm. This one also T12 at 100 mm, and the dimension of the footing is 2.3. Already know we know already. So this is 2300 mm, and this one is 2300 mm. Okay, now we have calculated this manually. Okay, now I will note down the some important values for the comparison purpose. So here is our Excel sheet. Here I will note down the manual calculation values. How much it is? Upward soil pressure, how much? Here it is 207.93, or we consider 208. So I will consider here 208. Effective slab thickness, how much it is? This is for 2A shear. Okay, wait a minute. For 2A shear, effective slab thickness, D effective, how much we considered? We have considered here. Here is 2A shear. Here we have considered 544 mm. So I will note down here 544 mm. And effective punching perimeter, how much it is in 2A shear? Effective punching perimeter length, here it is B dash 3096 mm. So I will note down this one 3096 mm. And cover we have considered, how much it is? 50 mm plus 12 by 2 6 means 56 mm. Okay, so tau v in 2A shear, tau v is 0.869 and tau c is in 2A shear, tau c is 1.118. So I will note down this 1.118. And punching shear ratio, how much it is? 0.869 divided by 1.118. 0.869 divided by 1.118. 0.77. Okay, 0.77. Now for one way shear, how much it is? Tau v value is for one way shear, where it is? Here is our one way shear. See, here is one way shear. Tau v is 0.281. 0.281. And tau c tau c is for one way shear. How much value is this one is 0.3104. 0.3104. Okay. So I will save this one. Now we will calculate this in Excel sheet. Okay. So this is our Excel sheet which is prepared by us only. So here we will use the same values. What we have considered here, dead load is 700, live load is 300. So dead load is 700, live load is 300, and width of column and depth of column, how much we have considered? Width of column 230, depth of column 230. So I will do here 230, 230. Okay. And FV 500 we have considered, and M20 we have considered. Okay. So this is FV 500, M20. SBC how much we have taken here? 250 kilonewton per meter square. So 250 kilonewton per meter square, and allowable settlement is 25 mm they given. So our extra percentage we have considered here in manual calculation 10%. So I will use here also same 10%. Okay. So now you can see here required area is 4.4 and length of footing required is 2.1 meter and width of footing is 2.1 meter. Here what action we have to do? Here I have written round up. Round up means 2.1 means I will round up to 2.3, and width of footing also 2.3. So depth of footing is 1.5 meter. So our area is 5.29 provided area. You can see here also 5. Where it is? Area provided 5.29 meter square. Okay. So and then SBC and net upward pressure. This is required 250 but provided 207. So this is less compared to SBC. So it's coming the safe. You can see here if I click this one as 1.9, then you can see there unsafe. So I will do 2.3, 2.3. So safe. Now depth required is 250. So double the values almost. So what I will do? I will consider in the here how much we considered here. D is 600 we have considered. So I will write same 600. I will take 600. Okay. So what happens here? You will get the effective slab thickness D effective and actual self weight of footing and percentage weight by percentage of loading 7.935. So we have provided 10%. If this one is maximum, it will take automatically maximum value only. So don't worry about that. And clear cover 50 and die off bar we have considered 12 mm. Okay. So what happens? AST required. How much we got here? AST required. Here it is 1702. And here, sorry, something is problem, I think so. Okay, maybe some due to digits and all, it is nearby 1701. Almost 20 mm square is less. AST minimum is 1656. So in our case 1656 AST minimum. So how much it's saying? Spacing required is 155. So I am rounding down to 100 mm. Then AST considered will become 16. By comparing these two, it will consider here 1681 and provided AST is here 2601. You can check here how much it is provided, 2601. So AST required should be less than AST provided. So in our case, in this you can see here, if this AST required is 1681 and provided is 2601, so it is safe in flexure, it's saying. Okay. So now in one way shear, how much it is tau v value? We have already calculated here. Tau v value is 0.281. Now you can check in Excel sheets 0.28. Tau c is 0.31. In manual 0.31, hence safe in one way shear. Okay, so here you can see safe in one way shear. In two way shear, check this effective punching perimeter 3096. In manual calculation you can check here 3096, here it is b dash value. Okay, and then tau v value for two way shear, how much it is in manual calculation? 0.869. So in Excel sheets 0.87, almost nearly. Okay, and ks tau c 1.12. In manual calculation, ks into tau c, how much it is? Here it is ks into tau c 1.118. Here 1.2 we got. Okay, round up value. So safe in two way shear. You can see here final schedule. How much it is? Length of the footing is 2300, width of the footing is 2300, depth of footing is 600 mm. You can see in this figure also. You can check here, and this here it is upward soil pressure 207.94, and along length and along width provided reinforcement is T12 at 100 mm. You can see in this figure also. Okay, this is what we have compared the values in Excel sheets also. So now I will note down these values. How much it is? This one is upward soil pressure is in Excel sheet. How much it is? 207.94. 207.94. And effective slab thickness is in two way shear, it is almost same, 544. And here effective punching perimeter b dash is, where it is in two way shear, effective punching perimeter 3096. Okay, so I will note down 3096, and clear cover will be the same one. Okay, now tau v value is in two way shear it is. Okay, in two way shear tau v value is how much it is? 0.87. So I will note down 0.87. And ks into tau c, how much it is? 1.12 in Excel, 1.12, and ratio will become 0.87 divided by 1.12. Sorry, 0.87 divided by 1.12, 0.776, 0.776. So round up 0.78. Okay, in one way shear tau v value is here, one way shear tau v value is 0.28, 0.28, and tau c value is 0.31. Okay, now we noted down the manual and Excel values, important values. I will save this file. Now let's model this in SAFE software. Okay, so here I will take this as new model. Use built-in settings. Take this display unit as metric SI and India, Indian, and here steel design code is not available in this SAFE software, Indian code. So you can take anything, it doesn't matter. And concrete design code is IS456 2000. Click on OK. As of now I don't need the grid, so I will use this blank spacing. And here model datum, in model datum I will use as 0, and story height above I will take it as 1.5 meter from up to ground level. Okay, so this one is story height below means 0. It is used in pile design, so it is not necessary. And model datum name what I will write is foundation. At 0 level we will write as foundation, and story above is ground level. After 1.5 meter ground level will be available. Ground level. Okay, so this one is, you can say base or 0 something, you can write anything. So I will click on OK. Now I will define the material properties first. Just go to define material properties. I will write down what material I needed in concrete. I need M20. Okay, and in steel I will use rebar and Indian. Here I will use, we have FE 500, so I will use this HYSD grade 500. Okay, okay. Now our material properties defined. Now I will define the section properties. Go to define section properties and slab sections. Here I will delete this property and I will modify this slab property. We need footing, so what I do, I will name it as footing FT. How much our depth is? 600 mm. Footing depth is 600 mm, we already know, and M20 grade of concrete. Okay, so slab material is M20, I will choose, and here it is shell thick. Membrane versus shell already I explained in ETABS course. You can enroll for detailed discussion in, for the superstructure also we have ETABS course, and here you are looking this detailed manner of this footing also. So you can enroll our courses, which is present in the www.phbconsultants.in. We'll write down. So www.phbconsultants.in. You can check here, or okay, it's okay, you can check here. We have ETABS course also and safe also. Now let's come to this what we did, define material properties we did. So here I did M20 and HYSD 500, so I will rename this as FE 500. Okay, or else I will delete this one. Another time I will add new material, rebar Indian HYSD 500. Here I will do FE 500. Okay, and in define section properties we need slab section, so I will delete this one and I will modify this one. You can add new material and you can do like that also. FT 600 M20, here M20, and here we need to use shell thick. I already explained membrane versus shell in ETABS course, and also it's present in YouTube video also. And shell thin, in shell thin and shell thick present. If slab's thickness is, let's say, length divided by 10 or width divided by 10, which will be less, the thickness of that slab is less than the L by 10 or W by 10, then we will use it as a shell thin. And if the slab thickness is greater than the L by 10 or width of the slab divided by 10, then we have to use the shell thick. It's just one, I made the rule. Okay, so but usually in footings we used to take this as a shell thick only, not shell thin and membrane. Okay, so in shell thick, so we have to choose the shell thick now. Okay, and here I will use footing, and how much we have, depth 600 mm. Okay, and now I will define stiff area, because we are not using the columns here. Okay, so what I will do, I will define the stiff area. Stiff area means, click on add property and stiff area depth is, you can use any depth, but I am using here depth of the footing and stiff area is same, M20. I will name it as M20, and here it is M20, and here in stiff area we have to use the membrane. Don't forget this one, okay? In stiff area we have to use membrane. In normal footing slab we have to use the shell thick, okay? So here I will select stiff and 600. Okay, actually thickness doesn't matter in stiff area, but still I will use the same as footing depth, okay? So let's say okay. Now I will define the spring, SBC, area spring. Here add new material and add new property, and I will name it as SBC 250. How much it is? They are giving the what we call it as, they are providing the 25 mm settlement. They are allowing the 25 mm settlement. So what I do, at 25 mm SBC, okay? So here subgrade modulus formula is, our SBC is 250, okay? I will divide it by, if our allowable settlement is 25 mm, then I will do it in meter. So 0.025, enter. This is our subgrade modulus, and keep this as same compression only and click on OK. Okay. Now define load pattern. Here dead is equal to 1, live is equal to 0, okay? Don't change anything. And then load combinations. In load combinations I will use as live load, 1 live load. I am not using here 1 dead load plus 1 live load, because I want to validate the manual design and Excel also. For that purpose I am in that it's 10% of extra loads we are taking as a self weight. So if, and our original self weight is almost, it's around 7%, so it doesn't match if we take that one. So for validation purpose only I am taking this as only live load, and I will take that self weight as 1100 load. You can see in upcoming steps, okay? Don't worry, I will use this as live load, 1 live load. Here I will take this as 1, okay, and add new combo 1.5 live load. Here I will take this as live 1.5, okay. Okay, now load combinations all set. Now I will do the modeling. For modeling I need the at least one joint or one node. For that I will click on the draw joint objects. You can click anywhere, so I will click here. Now you can see here one node, or whatever you can say, joint something, anything, okay? So now I want to model the footing around this joint. For that purpose I will take this option, quick draw area around the point. Here I will select the property slab property, footing property 600 M20, and in X direction how much we have? We have 3000. Sorry, not 3000, it's 2300, and Y direction also 2300. So I will do I think I will remove this one. I will get, okay. So here 2300 footing area 2300. Trim at slab edges I will explain in further classes. Now you can keep it as yes or no, whatever you want. Now footing area slab is modeled. Now I will draw the stiff area. How to draw stiff area? Same, we have to take this and here rectangular, and here property I will, here it's not visible stiff area, so I will use the none option. And how much it is? Column dimensions 230 and 230 in our case. So I will draw this here. Now I will correct this stiff area. We used none property, so for that I will change that into stiff area. Here I have defined already stiff area, so I will use this one. Now you can see here in 3D view, you can see here what's happening here. You can check here, stiff area is above the footing. For that, what I have to do, I will click and stiff area, mouse right click, and I will use this cardinal point to top. Now you can check in 3D. See here, now it's inside the footing only. You can visible now. Okay, like this we have to. Now I will take normal view. So I will untick the extrude shell and I will click on OK. This is our normal view. Okay. Now I will assign the SBC for this area, slab area. So I will select this one and go to assign and shell, and here area springs. Here I will choose SBC 250, apply. Here you can see SBC is applied. Now what I do, I will mesh this slab. Click on this footing slab. You don't need to select this stiff area. You just want to apply. You need to apply the mesh at the only slab area, not this stiff area. Okay, so what I will do, I will select this slab area, this footing slab area, and I will go to assign shell, and here floor auto mesh, and here I will choose this mesh objects into, let's say 2020. You can take 1010 also. Apply. Okay, now you can see mesh also applied 20 by 20. You can also see like this. Go to set display option, and here you can see shell analysis mesh, apply. Here it is visible. And one thing is very important, in center, in columns center where we draw the joint or node, at that point the meshing should be passed. One horizontal and one vertical should be passed. Okay, this is very important for load distribution. Okay, now I will untick shell analysis mesh and apply. Okay, now what I do, I will assign the load. How to assign the load? I will select this joint and assign, go to assign and joint loads, force. How much I will assign the load? Here I will take it as a live load. Okay, here in live load I will apply the total load. How much it is? 1100 is including self weight, dead load plus live load plus self weight of the footing. All we are applying here. So it should be in minus. So this is used for punching purpose. So dimensions in mm is 230 in x direction column and 230 in y direction. So I will apply. Okay, now you can see here in 3D view, you can see if it's not visible clearly, then you have to go to options and I think here only. Okay, here what I will do, I will do 15, and here also I will do 15. Click on OK. Now you can see here 1100 load is applied in the downward direction. Okay, so now I will go to plan view. Now I will do view revise preferences. In design, concrete slab beam designs, here view revise preferences. Here we have to change the preferences. Here you have to see the IS 456-2000 is present or not. Here you can see here design code, and in minimum cover slab we are using 50 mm, and here also 50 mm. Sorry, 50 mm, and here preferred bar size is we are using 12 mm. We already know na. See here we are using the 12 mm, so I am considering here 12. Okay, so here IS 456. Okay, click on OK. Now go to design, concrete frame design, view revise slab flexural design overrides. So here I have to select this slab and then go to design, concrete frame design, flexural design, finite element based. Here I will choose the FE500 we are using. So for that I am choosing this FE500. Okay, so now design, concrete frame design, select design combination. In design combinations we need 1.5 live load for the design purpose. So I will choose this one only and I will click on this mark. Okay, now design combination also selected. Now I will check the model. How to go to analyze, check model, select all. Okay, Wait for a minute, we'll check. Okay, our model has been checked, no warnings messages were generated. Okay, now what I will do, I will design. Here I have to go analyze, and here run analysis and design. So before this we have to save. So ours is module 1.1. Yes, I will save this one. Now it will run analyze and design the model. We have to wait for that. Now you can see here, first we will do upward soil pressure, we will check how much it is. So how to check? Go to display and go to show force stress diagram, and here soil pressure you can see here. And for upward soil pressure we need only unfactored load combination. So I will take this as one live load combination and click on apply. Okay, now you can check upward soil pressure. How much it is? Here it is 204, 205, 205. Highest how much it is? Here 207, 208.248. So I will note down how much it is. 208.24, 208.24. Now you can see here manual 208, Excel 207.94, in safe 208.24. okay, so now it's under the SBC 250. So this model is okay. Now we have to check the settlement also. It should be within 25 mm. How to check? Go to where it is, display and show deformed shape, and use this combo as one live load. Apply. Okay. Now you can see here how much it is settlement. In user direction you can check here in pop-up box how much it is, minus 20.49, and here you can check here how much it is, 20.56. in center of the column how much it is, 20.825 at the center of the column. So it is less than 25, hence okay. Now we will check for punching. How to check? Go to display, show punching shear design. How much it is? 0.775. Now we will see detailed manner, in detailed manner. Okay, so I will select this point joint and I will right click the mouse. Now you can see here pop up the calculation. See here, first we have to check here the column location is interior or not. If it is not considering the interior and ours is our column is present at the center of the footing, then we have to choose this column location as interior. If it is not present, then we have to change this as interior. How to change? I will explain that one also, don't worry. And here you can see here average effective slab thickness is, it's showing 538, and how much in our case, how much these are values, 544. okay, so in here it's considering 538, and the effective punching perimeter is here in safe 3072, in our Excel and manual 3096. So here it is not considering rightly. So our cover is 56 mm in manual and Excel, but here it is considering how much it is, 62 mm. It means it's not dividing that 12 by 2. For that what we have to we will change this one, so we will get the right answer. Let's check. Okay, so if I change this, override this, I will go to view revised preferences, and here I will change this as 12 to 6, 12 by 2 na. Okay, I will click on OK, and I will, and another one I will, that one also explain. If that column location is not interior, at that time what we have to do, we have to select this point and go to design and concrete slab design. Here view revise slab punching overrides, here we have to change this location to interior. In our case it's considering interior, so no need to change, just for the knowledge purpose I have told here. Okay, now I will do run analysis and design. We already changed the effective depth, sorry, die of the bar. Okay, now after design we will check this. Now display show punchings here. Now I will select this joint and I will right click, mouse right click, and zoom it to 150. So here now you can see here how much it is. Effective slab thickness is 544. Now you can see we got the same value 544, and effective punching perimeter in manual Excel 3096. In safe how much it is now? Now it is 3096. Okay, 3096 we will write down, and then here it is cover is 56 mm. Now here also 56 mm I will do. Now let's check the maximum design shear stress, tau v 0.85 in safe. In Excel and all it's little bit high. Okay, in this is concrete shear stress capacity Ks into tau c. How much it is in safe? How much? Concrete shear stress capacity 1.12. 1.12. Okay, now punching shear ratio how much it is? We know here 0.761. 0.761. Okay, now all okay. Now we have to provide the steels. Before one way check we need the steels. So for that purpose what I will do, I will draw the strips. So I will unlock the model and I will click on this draw design strips. Here I will take this as strip layer as B. So this is our along width. I will take this as B strip, and if this is B, I am doing this as B, then how much this length divided by 2 we have to do. It means 2003 divided by, sorry, 2300 divided by 2. It means 1150. Right? Same here also 1150. Start width left. It means start width here. Here it is start width. Start width left means here this one. How much it is? 1150. It means 2300 divided by 2. 1150. Start width right. This is the starting point. And this one is end width 1150. So I am drawing this. For this purpose I need this value and this value. It means this length divided by 2 value. Here I am not getting the center point, so what I will do, I will use this mouse select object and I will click here, right click and mouse right click, and here I will take this as snap option, and in snap option I will click this line ends and midpoints, apply. Okay, now I will draw the strip. Now this is strip B, strip layer B. Okay, how to see we have drawn the correct strip? In this case it's almost for both direction it's same, but in rectangular footing and all it will be changed. For that purpose you have to check like this, click on the set display option, and here you can see other assignments. In other assignments show width and apply. Now you can see here, if you can see here, if you did wrong means then what happens here? If you drawn this strip, here you did 1 point, in one side 1 point you did, and end width also one side 1 meter, then what happens? You can check here. See here, here is missing the strip width. So like this you have to check. Okay, so what I will do, I will click on this and right click, and here I will do 1.15. Here also 1.15. Click OK, and here I have to change this one also. Here it is rebar material, we have to choose the FE 500. Okay, okay. Now you got this strip. Now in this direction we need another strip. For this direction, what we have to do, here half, here half. So how much it is? The width of the footing is 2300 divided by 2. We are taking the full width. For that purpose, we are calculating like this. So here what I will do this as a strip layer A, and I will change this one as, I will draw this layer. Now you can see it's already, now we got in both directions strip layers. So I will off this show width, apply, okay. I have to modify this strip also. HYSD 500. It's already done. You can see here FE 500 I got. So now what we have to do, we have to do flexural design. Let's go to run analysis design. Wait for that. Now our design is complete. Now what I will do, go to display and here show slab design. Click on this. Here we are using the strip based design, so I will choose this as strip based, and display type is envelope flexural reinforcement. We don't want shear reinforcement, and I have to click this impose minimum reinforcement, so that it should be impose the 0.12% minimum where it is necessary. And in isolated square footing and all, we don't need the top rebar. For that we are not ticking this show top rebar. I will click on this show bottom rebar, and here reinforcing display type is I will choose this show total rebar area for strip, because I am considering full width of the footing. For that purpose I am using this option. And now I will choose this as layer B. First we will see layer B, and if I choose this as none, then it will show the how much total area required. It will show, it means 1883. 1883 means if we are using the, how much it is, 12 mm means, for 12 mm area is 113 mm square. So 113 divided by this 1883 multiplied by total this width of the footing, how much it is, 2300. I will show here. I will show roughly. Okay, so what we are doing here, how much it is, 1883 for this 1883 mm square we got. For this we are providing 12 mm means 5 by 4 d square. How much it is, 113 divided by 1883 into multiplied by how much it is, this width 2300. So 2300, the required spacing is 138 mm. So I can use this as 125 mm, round down. Okay, so similarly this is layer B. Similarly I will apply to layer A. How much it is, 1860 required. So 1860 means 1860 required. 113 divided by 1860 multiplied by 2300. So how much it is, 139 mm spacing required. So I will provide 125 mm for both sides. Let's check here. We have another option also here. You can see here, if I use this typical uniform reinforcement specified below, we are using the bottom, so I am using 12 mm. Here you can check like this also. You can put 250, sorry, you can check 300 mm is maximum. So I will apply for 300 mm. Still it required 993 mm square. So what I do, I will use 250 mm spacing. Still it required 820. So what I do, I will change it to round down into 200. Click apply. Still it need 560 mm square. So what I do, 150, apply. Now we need 126 still. So for that I will use 125 mm. Click on apply. Now it's vanished. It means we calculated manually also, na? You can see here how much it required, 125 mm. So at 125 mm it's vanished. It means we need 125 mm in this direction. Okay. Similarly for layer B you can check. Here I will do 250. Apply. Still need 840 mm, 842 mm square. So I will do 200. Click on apply. Still need 582. 150. Apply. Still need 149. So I will apply 125 mm. Full vanished. It means we need in this direction along width also 125 mm. T12 at 125 mm. Okay. Now we provided the at 125 mm. Okay. T12 at 125 mm we are providing. Now we got the shear, sorry, AST, we provided the steels. So now we can check the one-way shear also. For one-way shear, to know the one-way shear, check we need how much percentage of steel we provided. So we are providing the T12 at 125. You can calculate the PT. And the one-way shear will be at the distance of the D distance. So what I will do, D distance means how much it is, 544. How much it is, 544. So I will draw I will hide this one, hide select objects. Now I will draw the joints. Draw joints at X direction. How much it is? 544 from face of the column, and this center to this face of the column, how much it is? 230 divided by 2 means 115. 115 plus 544. How much it is? 659. So 659. I will click here, 659. Okay. From this to this 544 from face of this column. Okay. Similarly, in Y direction also we have same dimension. So what I will do, I will 659, I will click. So here it is. Now let's run analysis and design. Wait for that. After this, what we have to do, just go to display and show force stress diagram, and here strip forces. So first I will click show all objects, and then I will do display, go to force and shell, strip forces. Here I will take this combo as 1.5 live load, and here I use shear force, and for layer B I will click and apply. How much it is? 349.69. Okay. For layer B 349, and for layer A how much it is? 348.6, means both are almost same. 349 I will consider. So what I will do, now I will calculate tau V value. Tau V is VU by BD. VU is, we already know the from safe software, how much it is? 349 into 10 to the power 3. So our width is 2300, and depth is, sorry, effective depth is 544. How much it is? 0.27 Newton per mm square, or MPa is our tau v value. For tau c, we already know for the tau c value, but still let's do what we are doing. T12 at 125 mm we are providing. Okay, so AST provided is 5/4 d square by spacing into total width of footing. It means how much it is? 5/4, 12 square divided by 125 into 2300. How much the answer is? 2079. 2079 mm square is AST provided, but we need PT. For that, AST provided divided by B into capital D. How much it is? 2079 divided by 2300 multiplied by 600 into 100. How much it is? 2079 divided by 2300 into multiplied by 600 into how much it is? 100. The answer is 0.1506 PT. 0.156. Okay, so on this basis 0.15 PT, so we have to check in the table 19. In table 19, in IS 456 table 19, how much is our PT value? 0.1506. It means you can check here 0.15. How much it is? For M20, 0.28. So tau c is 0.28. Tau v is how much it is? 0.27. Tau v is 0.27. Tau c is 0.28. Tau v is less than tau c, hence safe in one way shear also. Almost when it safe in two way shear, then it's almost safe in one way shear also, so no need to cross check this like this. So I will write down here how much it is. For one way shear it is 0.27 is tau v and 0.28 is tau c. This is our comparison of the manual calculation versus Excel versus safe software. Almost all are almost same, not much difference. Okay, no one will explain like this, so we are trying to explain in depth with software knowledge. So for courses and all, please visit our website, which is, we have our own app also. You can search PHB Consultants. This is app name, and for website www.phbconsultants.in. Please visit for the courses. Okay, let's find. And the final our detailing is in manual, it's T12 at 100 mm in both direction, and in Excel also T12 at 100 mm at both direction. You can see here T12 at 100 mm in both direction. Similarly, but yes, in safe you can see here T12 at 125 mm in both direction. here we can check show slab design, and here if you put the T12 at 150 mm, click on apply, then it's required still 149 mm square. So what I do, I will use 125 mm, so it's passing at the 125 mm. Strip B. Now strip A, layer A, how much it is? I will check 150 mm. See, still it requires 126 mm. So what I do, I will put this as 125 mm. So it's passing now. Okay. So this is our comparison. This is our comparison for manual, Excel and Shape software. No one will do like this. Okay.